We're going to have a look at 3 different AS maths exam questions. The first of those is going to be to do with differentiation from first principles. The second of those is going to be to do with an optimisation problem. And the last of those is going to be to do with a binomial distribution. Okay, so we'll start off with this differentiation by first principles. So it says differentiate f of x is equal to 3x to the power 4 from first principles. The first thing that we need to know is that in the formula booklet we are given the formula for differentiation from first principles. So the first thing I'm going to do is just write that down, and then we'll apply this function to that. So that formula that we would be given is that f of x plus h take away f of x divided by h will give us the derivative. Okay, now what we need to do is just substitute our function into this. So we've been given f of x and we want to find f of x plus h, take away f of x all over h. And if we were going to do that, then we'd be subbing x plus h into f of x. That would replace x with x plus h and give us 3 lots of x plus h to the power 4. Take away f of x, well f of x is just 3x to the power 4, and all of that will be divided by h. So subbing in our function, or using our function with that formula, is going to give us what we've got here. Okay, I remember that with differentiation by first principles, that's in fact looking at the gradient of a chord, and we'll come and think about what we're going to do with h in a little bit. First, we need to actually look at how we can simplify this as much as we can. Okay, so first thing I'm going to do is I'm going to look at the expansion of x plus h. So x plus h to the power 4, if I was going to expand this, and we could use binomial expansion to be able to do this, this would give us the following expression: x to the power 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the power 4. So we're going to look at then substituting what we've got here into that, and then we're going to have a go at then simplifying this as best we can. So if I substitute this into there, that is going to give us 3 lots of this, take away this, over h. So 3 lots of all of that will give us 3x to the power 4 plus 12x cubed h plus 18x squared h squared plus 12x h cubed plus 3h to the power 4. So this is all of this just multiplied by 3. We're going to take away 3x to the power 4, and the whole of that is divided by h. And then we're going to look and see if we can simplify this in any way. So we can see we've got 3x to the power 4, take away 3x to the power 4. So those two terms there are going to go. And for every other remaining term, we can divide it by h. So we don't need to then write this as a fraction anymore. And if we divide every term by h, that would then give us 12x cubed plus 18x squared h plus 12x h squared plus 3h cubed. So this is what we've got. Now, once we've got it into the simplest form, we then need to consider what's going to happen to h. Now, we want this chord to become and to represent the gradient of the tangent. And to do that, or to get that as close as possible, we want h to tend to 0. Because remember, we said h was going to be the width of the gap making up this chord. So we're going to write now that as h tends towards 0, the gradient of the chord approaches the gradient of the tangent at that point. Then we need to consider what that would actually be. If we can see if h does tend towards 0, this term, and this term will all become 0. So we are only left with this term here. So we could say that the derivative would be 12x cubed. Okay. And if we know how to differentiate in the normal way, using the Leibniz notation, then we'd also know that times them by 4 there will give us 12x cubed. So we can check our answer from the top and just make sure that's exactly what we thought it would be. Okay, so that's how we differentiate from first principles for this question here. The second question that we are going to look at, like I was just saying before, is one that is going to be to do with optimisation. So it's going to be a minimising or maximising problem using differentiation. And this is the one here that we're going to be looking at. So it says a company plans to manufacture a flour shaker with a capacity of 200 cubic centimetres. The company models the flour shaker as a cylinder with base radius r centimetres and height h centimetres, attached to a hemisphere at one end as shown in the diagram. So this is the flour shaker that they're looking at modelling. It can be assumed that the flour shaker will be made from a material of negligible thickness. For a sphere radius r, the surface area formula is given here and the volume formula is given here. And we are looking at showing that the total surface area of the flour shaker is this. So this is what we're looking at arriving at. We're not going to use this in our working, but this is what we're aiming for. We've got the formulas for both the surface area and the volume of these two shapes here. And we have been given the volume of the total shape as well. Okay, and it's just worth noting here, we can see the surface area there and the formula we're aiming for, we can see it's just in terms of r. So the area is equal to this. So the first thing I'm going to do is we're going to look at this shape and we're going to work out how we could form an expression here to represent the surface area of this shape. So let's break it up. We've got two things here to work out the surface area of. So I guess we've firstly got the surface area of the hemisphere. Now, if we were looking at finding the surface area of the hemisphere, we know to find the surface area of a sphere, we can use 4 pi r squared. But the hemisphere, the surface area, that will be half of that. So we'd be looking at finding a half of 4 pi r squared. So 2 pi r squared, keeping it in terms of r because our radius is r, would represent the surface area of the hemisphere. The next thing is then to think about our cylinder under here and to think about how we could find the surface area of that. So the surface area of the cylinder, obviously that would only include the area around the outside and the area at the bottom. So we've got pi r squared would be the area of the circle at the bottom. And to find the rectangle that wraps around the outside, that would be the circumference times by h. So we can use 2 pi r as the circumference and times that by h. So 2 pi r h would represent that. So that would give us 2 pi r h. And then if we add on pi r squared, which would represent the area of the circle at the bottom. So this would be our area of the cylinder. So actually, the total surface area, we can then write down a formula for that will be these added together. So that, add that. So we've got 2 pi r h plus pi r squared plus 2 pi r squared. These two, and simplify and collect these two terms together, then that will give us 2 pi r h plus 3 pi r squared. Okay, so this is our expression here representing the surface area of this shape. Now, at the moment, we can tell that obviously is not exactly the same as this. There's something more we need to do here. And one of the key things and reasons behind this is because this has got an h in and this does not. So we need to change h. Now, if we look back at the question, that we can see there is a bit of information that we haven't used. We were given the volume of this shape. We haven't used that in any way yet. So let's see if we can form an equation representing or using that fact, and let's see if that's going to be useful in any way. Okay, so we know that the volume is going to be 200, centimeters cubed. And let's see if we can then equate that to how we'd find the volume of this shape. So obviously if we're finding the volume of the sphere, we're going to be using this formula here, but we have got a hemisphere, so we're going to need half of that. So the volume of the hemisphere would be a half of 4/3 pi r cubed, and then we'd be adding on the volume of the cylinder. For the volume of the cylinder, we will find the area of the base and we'll times that by the height. So that will be pi r squared h. So that there gives us the volume of our shape here, the total volume. Let's simplify this slightly. Just by timesing by this, which will give us half of 4/3 will give us 2/3 pi r cubed plus pi r squared h. Now the first thing to think about here is what we've got. We have got a equation, and this is in terms of h, and this is in terms of r. So the plan of action here is going to be that if we can rearrange this to get h as the subject, then we can use this and sub this in here to get this equation for the total surface area purely in terms of r. Okay, so let's think about how we rearrange this to get h as the subject. First thing I'm going to do is I'm going to times every term here by 3. So times everything by 3, it's going to give me the following. Then I'm going to subtract this term here. So I'm going to take away 2 pi r cubed from both sides. And then now I'm going to divide by 3 pi r squared. See what I've got there. Okay, so now we have got something, an equation for h in terms of r, and we're going to then substitute this back into the expression we had there for the total surface area. Okay, give me a little bit more paper, so I'll come and write some of this below. Okay, so if we substitute this back in, we're going to look back at this here, the surface area that we've got, and then we're going to be subbing in everything we've got here into this. Okay, so that is then going to give us the following: 2 pi r times by everything we've got here, because we're going to add it. So 600 take away 2 pi r cubed over 3 pi r squared, and that is going to be then added to 3 pi r squared. So that now is our expression for the surface area purely in terms of r, and the only thing we need to do here now is simplify this, and we're going to hope that it is going to bring us out at the formula here that we were told to show. Okay, so first things first we can do here, we can times all of this out by 2 pi r. So if we times everything in the bracket there on the numerator by 2 pi r, that is going to give us 1200 pi r take away 4 pi squared r to the power 4 over 3 pi r squared plus 3 pi r squared. Okay. Then we can look at where we can go from here and what we can do and how we can go about simplifying this. What I would do is, because here we've got is just 2 separate fractions, I would actually separate what, the fraction here and then look and then see how we can simplify that. So I'm going to write that separately. So we've got 1200 pi r over 3 pi r squared, take away 4 pi squared r to the power 4 over 3 pi r squared plus 3 pi r squared. Then we'll look then and think about how we can simplify this even further. So we can divide by 3 here, which is going to give us 400. We can divide by pi, so it'll cancel completely, and we can divide by r. So that will give us 400 over r. And for this one here, we can divide by pi. So that's still going to leave it as 4/3. But we are going to have a pi on the numerator. And we also can divide by r squared, which will leave us 4 pi r squared there. And we've still got plus 3 pi r squared. Now, we can't do anything and simplify this in any way, but these two we can add them together because they're both terms with pi r squared. So we can take 4/3 away from 3, which is going to give us 5/3. So that will leave us with 400 over r plus 5/3 pi r squared. Which is, if we look back, it's the original thing we wanted to prove. 5 pi r squared over 3 plus 400 over r is exactly the same expression that we've just got down to for the surface area. Okay? So we firstly had to form an equation representing the surface area, realise that that was actually in terms of h as well as r, and then use the piece of information there that we were given to be able to find it just in terms of r. The next part of this question, and keep the other one close because we're still going to be able to need to use what we've got there for this next part, says, in order to minimise the cost of production, the company wishes to minimise the surface area. Find the dimensions of the flour shaker when it has the minimum surface area. Fully justify your answer. So we're going to be using our equation for the surface area, and we're going to be looking at minimising this. Now, if we're looking at minimising this, we need to find a stationary point. We need to show that it's a minimum, and we need to find the values for this. And this has told us to find the dimensions, so we want both the radius and the height for this. So using the formula that we already have, I'm just going to write this at the top. We said that the area is equal to 5 pi r squared over 3 plus 400 over r. So the first thing we're going to do is going to be to differentiate this. So if we differentiate this, we will get dA by dr, and that will give us, if you times by down by the 2, that will give us 10 pi r over 3. And note that this could be written as 400 r to the minus 1. So if you times by the minus 1, it will give us negative 400, and lower the power to minus 2. So that will be the same as take away 400 over r squared. Now, to find our stationary point, we need to equate dA by dr to 0. So we want to equate that to 0, which will give us 10 pi r over 3, take away 400 over r squared equals 0. And then we'll look at then solving this. So let's add 400 r squared to both sides. So it'll give us 10 pi r over 3 is equal to 400 over r squared. And I'll work across here just to give us a little bit more room. So if we times it by 3 and then we'll times by r squared, then that will give us 10 pi r cubed is equal to 1,200. And then if we're looking at finding r, then we can divide by 10 pi. So we know that r cubed will be equal to 120 over pi. And finally then, if we cube root that, and we can use our calculator to do that, so let's find the cube root of 120 over pi, which will be 3.4 to 1 decimal place. Okay, and don't forget that that is going to be the radius. This is in centimetres here, so that will be 3.4 centimetres. We've only got one, so we're only looking and checking that this is the minimum value. But notice that it does say find the dimensions of the flour shaker, so as well as wanting the value of R, it would also want the value of H. So I'm going to use the formula that we found for H here in the previous question, and I'm going to substitute R back into there to find our value of H when R is 3.4. We can do that by submitting it in there. So H is equal to 600, take away 2 pi, lots of 3.4 cubed, all divided by 3 pi times by 3.4 squared. And if we find the value to that, then that will give us 3.4 also. Okay, so at the moment for this stationary point, both the value of R and the value of H are 3.4. Now we haven't quite finished because at the moment we haven't shown that this is a minimum point. We need to show that these are the dimensions that give us the minimum cost of production, and we'll do that by finding the second derivative. So if we find the second derivative of this, then that will give us 10 pi over 3 plus, and we'll times down by minus 2, so that'll be 800 over R cubed. Now to show that this is a minimum point, we are going to need to show that the second derivative is greater than 0. And that will require us putting R equals 3.4 into that. So when R equals 3.4, we can say that the second derivative is equal to, and if we substitute 3.4 into what we've got there, that should give us on our calculator an answer of 30.8. That is greater than 0, which is what we hope for. So because that is greater than 0, we can say hence it is a minimum value. Okay, so we've shown there that it is a minimum value. And the last part of this question, the very last bit, is for part C. It has asked the following. It has said, state one limitation of the model and suggest an improvement. And I think the key thing for this to think about the limitation would be to look back at the question here. Because one part of the question here says, it can be assumed that the flour shaker will be made from a material of negligible thickness. It's always worth going back and looking at the question and see whether any assumptions were made, because obviously assumptions will affect the model and can be a limitation of that model. So in this case, we are going to explain that actually that would be a limitation. So we will say that the thickness of the material has not been taken into account, so the dimensions are smaller than they would be in reality. Okay, so the dimensions are smaller than they would be in reality because that thickness of material has not been taken into consideration. Obviously, if there was a thickness, then the height of the whole shape, the radius, everything would be larger here. And we'd have to consider this really to get a better, more accurate representation of the cost here. So that would be our limitation. It does suggest an improvement. So based on that, we could say that an improvement would be using a model that includes the thickness of the material. Now obviously in this case, to simplify the model, they assume that the thickness was negligible, but to make our model more accurate, it would make sense to include the thickness of that in our model itself. Okay, so that's the last part of that question there. And the final question that we're going to look at is one to do with a binomial distribution. So for this question here, we have been told or shown that this is going to be a binomial distribution here. We've got a value of n as 5 and the probability we don't know, we're not given. We're told that the probability that x is equal to 3 for this distribution is equal to the probability that x is equal to 4. And we've been told to use that to find out the value of p, given that p is greater than 0 and less than 1. Now usually we're given n and p and we're asked to find a probability or something like that, but in this case this is kind of turned on its head. We're coming at it from the other way here. We can't find the probability using, the probability here using our calculator if we don't already know that. So we need to think about this a different way, and I'm going to write down the original formula that you will have looked at when doing the binomial distribution that we can use to find a probability also. But usually we would use our calculator in most cases instead, but this will also still find the exact same probability. Now, if we look at this, we can substitute our values into here for both x equals 3 and x equals 4 to find the probability, and we know that the two probabilities are equal to each other. So we're going to substitute in what we know, and then we'll see if we can then find out and solve this for p. So n choose r, so for the first one here that will be 5, because n is 5 and r is going to be this value here is going to be 3. So that will be 5 choose 3. The probability raised to the power of r, which would be 3, and 1 take away the probability raised to the power of n take away r, 5 take away 3 is 2. That's then going to be equal to the probability that x equals 4. So this time that will be 5 choose 4 times by the probability to the power of 4 times by 1 take away the probability to the power of n take away r, which will be 1. So this is what we're given. We're going to start to simplify this, and we'll do this by working out the values of 5 choose 3 and 5 choose 4. So 5 choose 3 is going to give us 10, so that'll be 10 lots of p cubed times by 1 take away p squared, and that's equal to 5 choose 4, which is 5, lots of p to the power of 4 times by 1 take away p. So here we've got an equation that we're then looking at solving for p. There's something really important in the question here that we're going to need to be able to use, and that is that at the top it's told us that p is greater than 0 and less than 1. So p cannot be equal to 0 and p cannot be equal to 1. Now if we were looking at solving this, if we were going to solve something like this and we had p cubed, p squared, it would give us a solution of 0. And for 1 take away p, it would also give us a solution of 1. Those can be discounted. So normally when we're solving an equation, when we can't divide by anything involving p because we'll lose a solution, in this case we now can, because we can discard any solutions that would give p equals 0 or p is equal to 1. So I'm going to divide both sides by 1 take away p, and I'm going to divide both sides by p cubed. And if I do that, that will give us 10 lots of 1 take away p, which is equal to 5 lots of p. That's what we get when we divide by 1 take away p and divide by p cubed. And let's then see if we can go on to solve this. So expanding the bracket will give us 10 take away 10p is equal to 5p. And then if we add 10p to both sides, we've got 10 is equal to 15p. And if we divide by 15, that will give us p is equal to 10 over 15, which is the same as 2 over 3. So 2/3 there will be our solution for p. And we're only able to do that because we could divide by p and 1 take away p because of this at the top. And that actually comes into the second part of this. For the second part, 50b, it says explain how you've used that inequality in the answer to part B. So the way that we did that is that inequality didn't allow p P to equal 0 or 1. Okay, and because of that, these solutions would be discounted. And because they were discounted, that allowed us then to divide by p cubed and 1 take away p to allow us then to be able to solve that equation for p. Now, obviously, we could have expanded that all and we could have solved it anyway. Would have been a lot more complicated, but it would have still given us the same values. It would have, however, included values of 0 and 1, obviously, there for p. So it's much quicker being able to discount them and solve them in the way that we've done it.